So a key feature of organic chemistry at A level is the idea of organic mechanisms. That is a way of understanding better how reactions take place and why reactions take place involving organic molecules. And alkanes, which is what this video is primarily about, introduce us to our first mechanism. So to understand mechanisms, we have to appreciate how we represent the breaking of bonds using something called curly arrows. Now, the reason that we're doing this is because organic chemistry is in one sentence, and this is obviously a massive reduction, but the breaking and formation of covalent bonds. Bonds are breaking, new bonds are being made. And then we start with our reactants and we end with our products. So you've done covalent bonds at GCSE, and you described covalent bonds as a shared pair of electrons, and you represented them in when you did dot and cross diagrams with dot and crosses. So if you had a dot and a cross that was between two atoms, then that was a shared pair of electrons. Now a covalent bond, which is that shared pair of electrons, can break in two ways. It can break either homolytically or heterolytically. And those beginnings of those words, the homo bit means the same, and hetero means different. So we're going to examine those two forms of breaking in a little bit more detail now. So we're going to start with heterolytic bond breaking. So in this case, what happens is when the bond breaks, both of the electrons that are in that bond, both of the shared pair of electrons, will move to the same atom. So we're going to use chlorine as an example. So I'm going to represent chlorine initially as a displayed formula. So the line in between the two chlorines, that represents a covalent bond, that represents a shared pair of electrons. I'm also going to draw the dot and cross diagram. So both of these represent the same thing. That covalent bond there is that shared pair of electrons there. Now we're going to examine that bond breaking heterolytically. So going to have a product, and both what heterolytic bond breaking tells us is that the electrons move onto the same atom. So we are going to end up with a negatively charged chlorine ion and a positively charged one. So why has that happened? Because it'll be clear if we look at our dot and cross diagrams, what we are ending up with, we're saying that both of the electrons in the shared pair have gone onto one atom. Okay, so when we look at our dot and cross diagram, hopefully that makes that a little bit clearer. Both of the electrons in this example that were in the that were in the covalent bond have gone on to the chlorine on the left, and that means that the chlorine on the right has in effect lost an electron. It's electron deficient, so we end up with two different species, hence heterolytic as well, because we end up with two different species. So remember, homo means the same, so in homolytic bond breaking, one electron of the shared pair goes onto one atom and the other electron goes onto the other atom. So we end up with two species that are the same. So again, if I just start with my displayed formulae, and if I just draw my dot and cross underneath, then what happens is one of the electrons goes on one atom and the other on the other. So we're going to represent it like this. Okay, and perhaps it'll be a little bit easier to see on the dot and cross diagrams. So they're neutrally charged because they still have the same number of electrons as protons, but they have an unpaired electron. They have an electron that's unpaired or on its own, so I'm just highlighting them here. So that's what those dots in the top line represent, and they are called free radicals. Okay, So they are atoms with unpaired electrons. That's what those species that I've done in the two equations are supposed to represent. If I was to use arrows, which we're going to come to in a second, I would be showing that one electron went onto each chlorine, and I'm going to talk about this a bit more, but you'll notice I've used what I call a half-headed arrow, or I've used an arrow with only, it's like a fish hook. But we are going to talk about the arrows in greater detail in a second. So on the previous two slides I used arrows, and they were to represent the movement of electrons. We can represent the movement of one electron if we use a half-headed or fish hook arrow, so something that looks like this. Okay, and if we use a double-headed arrow, or what you would probably think of as a normal arrow, that denotes the movement of two electrons. This is going to be very important shortly when we look at mechanisms. And then finally, just to do primarily with this topic, or primarily to do with alkenes in a second, we would show an unpaired electron with a single dot. Okay, and that must be shown. We can only be confident or sure or certain that something is a free radical, has an unpaired electron, if we show that single dot. So we use Kelly arrows to sort of explain what happens in a reaction. And the analogy I like to use is you've typically, well, up to this point, you've looked at reactions and you've seen reactants on the left-hand side and products on the right-hand side. And then you've just had an arrow in the middle. So the reactants come together, the reaction takes place, and we form the products. And to me, that's a bit like reading the first page of a novel and the last page of a novel. So we know on the first page perhaps that these characters are present, and we know on the last page that this thing has happened to these characters. But what we don't get any sense of is, well, what happened? Why did that happen? Why did those two characters at the beginning end up being the way they were at the end? So you've got the beginning of the story, you've got the end of the story, but you haven't really got how the story happened or how it unfolded. And what mechanisms allow you to do is they fill in that missing bit in the middle. They allow you to see how those reactants came together to form the products that they did. So we typically use displayed or structural formulae when we're showing mechanisms and when we're using curly arrows, which are sort of explaining the story. It allows us to break a reaction down. So sometimes we might have a couple of intermediates. So we may have our reactants and we may have our products, but in between we may have a couple of different structures, sort of intermediate structures. So I'm just going to draw an example. This example actually probably isn't one that you would formally do yourself until maybe the end of year 12, but it's just really to illustrate the point really. So I'm going to react a ketone. So I'm going to have propanone because that's just fairly straightforward. Okay, so there's my propanone. And it's going to react with cyanide. And cyanide is an ion. One of the things that is going to become clearer is that if there is a lone pair of electrons and they are involved or they are part of the reaction, then we absolutely need to show them. So what will happen is the lone pair of electrons on that cyanide will attack. Okay, and it's because it's both of them, I'm showing it with a full-headed arrow. They will attack the carbon. We'll understand, or you'll understand why it's attacking that carbon in another part of the course. So I don't really want to talk about that, but it does. And then one of the pairs of electrons in the carbon-oxygen double bond will go onto the oxygen. So we show that movement. So then we have an intermediate. So we have our CH3, our carbon, our CH3. We now have a bond with the cyanide, because that's what that first arrow I drew was showing the movement of. And then we have an oxygen, but because we had the arrow going from the double bond onto the oxygen, we've got an extra lone pair there. And then we still get something else happening. So we might have added a second reactant. Well, we would have done in this case, we would have had an H+ ion present. We would have added a dilute acid. the pair of electrons that are on that negatively charged oxygen would attack that. So again, it's a pair of electrons being shown, pair of electrons moving, being shown, and then we end up with our final product. So what the arrows have done is they've given us a much better understanding of how the reaction has taken, how and why actually the reaction has taken place, what's actually happened. Now, like I say, that's the first time you've seen a mechanism. It's also a mechanism that we wouldn't look at in any detail until the end of year 12, but it's just really to show you at this point the role that arrows can play in explaining what is happening in a reaction. So now we're going to focus specifically on alkanes, and we're going to focus on a specific mechanism called free radical substitution. That's a type of reaction that alkanes can undertake. Now, alkanes are actually pretty unreactive molecules. Obviously, they can combust, and that's something that you did a lot of in GCSE. So the combustion of alkanes, because that's, they make excellent fuels. That combustion reaction is very exothermic. A lot of energy is released. That energy can then be used usefully. To actually get them to react with something other than oxygen is very difficult, but it is possible to get them to react with halogens under certain conditions. So here's just some example equations or example reactions where alkanes have reacted with chlorine. So on the first equation, we've started with methane, and we've reacted it with chlorine, and we've got hydrogen chloride, and we've got chloromethane. Okay, and then we can see that the subsequent reaction equations are increasingly removed, or taking another hydrogen, taking another hydrogen, taking another hydrogen. So if we look at the very first species, we start with methane, and it is possible, if we then proceed down all of these reactions, to end up with tetrachloromethane. Okay. Now we call this type of reaction a substitution reaction, and that is because we have replaced or substituted one of the hydrogen atoms with a chlorine atom. So if we see the very first equation at the top, methane plus chlorine produces hydrogen chloride and chloromethane. And it's not immediately clear from this, but we're going to see this, how this is repeated in other reactions. If we have an alkane reacting with a halogen, then for every one hydrogen atom that's replaced, one halogen molecule, so that X represents any halogen, one halogen molecule is needed and one hydrogen halide molecule is formed. So in the reaction at the top, we replaced one of the hydrogens in methane with a chlorine. We required one chlorine molecule to do it, and we got as a product one hydrogen chloride molecule. So let's just apply that knowledge in these three different reactions. So approaching this, I'm just going to put the arrow to represent the reaction, and I know that methane is becoming bromomethane. So I have to be confident about my structural formula here. So I am replacing one hydrogen with a bromine, so I'm going to need one bromine molecule, and I will also get one hydrogen bromide molecule. Okay. So that is very similar to the one on the previous slide. The one on the previous slide was methane and chlorine making chloromethane. This is methane and bromine making bromomethane. So it is essentially identical. It is the same equation, except we have bromine instead of chlorine. Let's just have a look at the next two, though, because they're slightly different. So for a start, it's not methane, it's ethane. That's our alkane that we're reacting. And also notice that we are making hexachloroethane. So this is where you've got to remember a couple of things from the introduction to organic. So hexa means there are 6 of them, and we know that we've got 6 chlorines. And then the eth, or the ethane, well, the eth tells us it's 2 carbons, and the ane tells us that it's fully saturated. So we are going from ethane, And I'm writing this as a structural formula, not a molecular formula. And it is becoming hexachloroethane. So every one of those hydrogens has been substituted or replaced by a chlorine atom. So we've got 6 hydrogens substituted, so that means we are going to need 6 chlorine molecules. So remember on the previous slide, for every hydrogen that's replaced, we will need 1 halogen molecule. And for every hydrogen replaced, we will make 1 hydrogen halide, so we are going to get 6 hydrogen chlorides here. We look at the one at the bottom, the final one. So we've got propane. So propane is CH3, CH2, CH3. And then they've given us the number 1,1-dichloropropane. So we've got to be careful about where we put our chlorines. 1,1 means that we put them on the both, well, and the dichloro tells us it's 2 chlorines. The 1,1 tells us that they are both on the first carbon. So 2 of those hydrogens on the first carbon have been replaced by chlorines. So hence CHCl2 instead of CH3. And then that is the rest of our molecule. So we have replaced 2 hydrogens. So that means we're going to need 2 chlorine molecules. And we have replaced 2 hydrogens, so we are going to make 2 hydrogen halides. So they all follow that, what was on the previous slide, they all follow that rule, and hopefully by just taking you through how the final overall equation was deduced, that begins to make sense, although I appreciate I could see what the structure of 1,1-dichloropropane would be a lot quicker than maybe you can at the moment, but that is something you will be able to do quickly at some point. So our equation at the top is like that. What I said earlier about it tells us the beginning, it tells us like the first page of the story, and it tells us the end, the last page of the story, but it doesn't tell us what's in between. We don't know what's happening to go from the left to the right. Well, in the case of alkanes reacting with halogens, it's going to actually involve 3 stages. Okay, and they are called initiation, they are called propagation, and they are called termination. So we are going to begin to understand better how we get from the left to the right via the 3 stages. Okay, that's what we're going to be looking at now. Now, I said earlier that alkanes could be made to react with halogens if the conditions were right. And the conditions that we need to have is the presence of UV light. So this word photon, I'm not going to really explore it. That's really, explaining what a photon is in great detail will take a very long time. But you know that light is a transfer of energy. And you know that depending on the frequency of light, we know whether that transfer of energy, we get a sense of how much energy is transferred. So we have one end of the electromagnetic spectrum, radio waves, where there is a low transfer of energy, and then right at the other end we've got gamma rays, high transfer of energy. You can think of a photon as a packet of energy, all right? So UV light is reasonably high energy, and a photon is like a packet of energy. So if that packet of energy is big enough, there is the possibility of it breaking a covalent bond. So when you've done, even at GCSE, you've done bond breaking, bond forming, you know that there's been these bond energy values. And so a certain amount of energy has to be put in to break a particular bond. Well, UV light provides enough energy to break the bonds in halogens. So what actually happens then is that our chlorine, I'm going to represent it like this, is going to split into 2 chlorine free radicals. UV light is the condition that needs to be present, otherwise it won't happen. And in effect, what is happening is, if I draw underneath I'm only going to show the electrons, the shared pair of electrons here. Okay, there are obviously 6 other electrons around each atom, but I just want to show, because I'm going to use that half-headed arrow because it's the movement of one electron. So we have our UV light condition and we end up, okay, so it says light must be of a high enough frequency and therefore energy. So that's why we're talking about UV light here. Visible light won't do it, infrared radiation won't do it either. So this UV light, which basically can be provided by the sun, or we can do it artificially, provides enough energy to split the chlorine molecule, and it splits it into 2 chlorine free radicals. And one of the things that we need to appreciate about free radicals is that they are very unstable, and that means they are very reactive. So initiation is simply the production of free radicals. Once those free radicals are made or formed, then the reaction with an alkane can take place. So even though alkanes are relatively stable molecules, get a free radical involved and they will react. So once the radicals are formed, then we can proceed to the next stage, which is propagation. So these chlorine radicals, because our example here is chlorine reacting with methane, are extremely unstable or extremely reactive, and methane can't help but react. And it happens in 2 stages. So propagation comprises of 2 stages. So stage 1. So we have our chlorine free radical and we have our methane, because obviously they are our reactants. What happens then is that chlorine free radical strips off one of the hydrogens on the methane, leaving behind a methyl free radical. Now what I'm going to do is, that free radical is on the carbon, which is why I have drawn the dot next to the C, and this is something that we need to be just mindful of. Okay, it is where we can, we should make it really clear where the free radical actually is. So it's on the carbon and not on the hydrogen. Okay. The second stage, so whatever free radical we have on the right of our first equation, that must be in the second. Okay. And then we are reacting with whichever halogen it is that we're reacting with overall. Well, it's chlorine, but we're doing it as the halogen molecule. And then what happens there is the methyl free radical strips off one of the chlorines in the chlorine molecule to make now our chloromethane, and that leaves behind a chlorine free radical. So things to note. So notice that on every side of both of these equations we have a free radical and a molecule. Free radical and molecule. Okay, that's something just to, I think it's helpful actually to realise that. Next thing is I'm going to add these 2 equations together. We've got Cl plus CH4 plus the methyl free radical plus Cl2. So that's all of the species on the left-hand side of the reaction arrows. And then on the right-hand side, you've got the methyl free radical plus HCl plus CH3Cl plus chlorine free radical. And then in maths, you would simplify, and in chemistry, you simplify. So you look for, do I have things on both sides that can cancel each other out? Well, I have the methyl free radical on both sides, so I can cancel that out. And I have the chlorine free radical, so I can cancel that out. So when we look then at our overall equation is the reaction that we were trying to do the mechanism to. So methane plus chlorine produces chloromethane and hydrogen halide. or hydrogen chloride, sorry, in this specific example. So that is our overall reaction equation. Something else to just highlight is, what would be a colour to use here? Well, yellow. Notice that we started with a chlorine free radical and we finished with a chlorine free radical. So our chlorine free radical was regenerated. So we can see that it's acting as a catalyst. So at GCSE, you spoke of catalysts being something that weren't used up. Well, we could refine it a little bit more. What we can say is they can be regenerated. So what you always find is that clearly this chlorine free radical has taken part in this reaction, but because it's regenerated, when we look at the overall equation, it doesn't feature in the overall equation. And that is also an absolute sign that a catalyst is present. So a catalyst never features in the overall equation because it's on the left-hand side and it's on the right-hand side, which means it cancels out, which means it doesn't appear in the overall equation. So our chlorine free radical was regenerated in the course of these two propagation steps. That makes it a catalyst. That also means that that chlorine free radical can go and the propagation steps can happen again with the same chlorine free radical, with that regenerated chlorine free radical, and the reaction can happen again and again. And so what actually happens as far as propagation is concerned is we get a chain reaction. So one chlorine free radical can end up resulting in a lot of propagation steps taking place. The third and final stage is called termination. Now, any of the radicals that are formed in any propagation steps, they could potentially collide with another free radical. And if they do that, they won't get regenerated. The free radicals will form a coherent molecule, a normal molecule, and that chain reaction, as far as those free radicals are concerned, will be broken or stopped, and hence the word termination. So if you think about what we had on the previous slide, there were two types of free radicals in our two propagation steps. There was a chlorine free radical and a methyl free radical. In theory, if we were only looking at those free radicals, a chlorine free radical could have collided with another chlorine free radical, and that would have made a chlorine molecule. A chlorine free radical could have collided with a methyl free radical, which would have made, interestingly, the product that our overall equation would have made. So chloromethane, sorry, that's a terrible H. And then the final possibility, and something to just be particularly aware of, is that we could have had two methyl free radicals collide, and they would have made ethane. Okay, so that's definitely something to be mindful of when looking at the possible products of a free radical substitution reaction. I mean, one thing perhaps to see from this is that even though we might have an overall reaction equation of CH4 plus Cl2 goes to CH3 Cl plus HCl, that's because we're focusing on what we're interested in. But in reality, when we have free radical substitution, there is very little control over what's ultimately produced, and there will be a huge variety of products. Even though termination takes place, that doesn't mean chain reactions don't necessarily just continue and continue. You have to think about the probabilities of two free radicals colliding. Now, it's going to depend a little bit on how much, say, the chlorine that you had in the first place, but let's assume that you had a lot more of the methane than the chlorine. That means you have far fewer chlorine free radicals than methane, which means that the probability of any of the free radicals that are formed colliding with another free radical is very small. And so, again, this is also one of the reasons why it's very difficult to control the reaction, because ultimately the only way the reaction can finish is either because all of the possible substitutions have taken place, or because all of the free radicals have collided with each other, and that latter doesn't have a high probability. So even just a very simple and straightforward reaction like methane with chlorine can give us 6 possible products. So we obviously could make hydrogen chloride. That would have happened in every one of the first propagation steps that took place. Chloromethane, that could have happened because of the 2 propagation steps, or because of a chlorine free radical and a methyl free radical. And then we could get further substitution because we're not in control of the reaction. So we could continue to substitute hydrogens with chlorines. We could eventually end up with all of the hydrogens substituted. And as we saw, if we had 2 methyl free radicals collide, we could get methane. So just that putting in a reaction vessel chlorine, methane, and having UV light shone on it is enough. We would get 6 different products. So I'm going to do another example. So here's propane reacting with chlorine to make chloropropane, or 1-chloropropane specifically, actually. What I'm going to do is I'm going to do all of the steps. So I'm going to do the initiation, then the propagation, and then the termination, to try and give you a complete picture of one particular reaction. So I'm going to start with initiation. So remember, initiation is the formation of the free radicals. We're using chlorine, so we are going to get 2 chlorine free radicals here. Okay, and then the next step is propagation. So the chlorine free radical is reacting with our propane, and we get one of the hydrogens removed, so we end up with our propyl free radical. And notice I'm putting the free radical clearly on that final carbon, which is the one which has lost the hydrogen. And obviously also I get a hydrogen halide, or my hydrogen chloride formed. Whatever free radical I have produced on the first propagation equation has to feature in the second. So I'm drawing my propyl free radical again, and making sure that it's clear where the unpaired electron is, so on that final carbon. It's reacting with chlorine. So then the propyl free radical takes one of the chlorine atoms. Okay, and that's why we then get our 1-chloropropane, and our free radical is regenerated. If I was to add those 2 propagation reactions together, I would get that overall reaction at the very top of the slide. Then our final stage is termination. So just going on our propagation steps that I've written and the free radicals that are present there, I could have 2 chlorine free radicals collide, come together to form a chlorine molecule. I could get our propyl free radical, and that could collide with a chlorine free radical to make our intended product, as it were. Or I could have 2 propyl free radicals collide, just fill it out, and that would make hexane. Okay, so just using those free radicals in the 2 propagation steps on this page, there could be 3 different products, although obviously the chlorine could take part in an initiation reaction again, so and it wouldn't look as though it was a new product, so there would be two possible products just on these propagation steps. But actually there's nothing to stop any of the molecules that we then make. So if we think about the main ones that we make in this are the 1-chloropropane and the hexane, they could start the chain reaction, they could be a part of a new propagation step. We could have 1-chloropropane with a chlorine free radical and end up with 1,1-chloropropane or 1,2-chloropropane or 1,3-chloropropane, and so on and so on and so on. There are many, many products that could be produced here. And just really highlighting that, to highlight the fact that there's very little control over free radical substitution in terms of what we're making, to give the sense that there will be multiple products. If we just take methyl propane as an example, simple branch chain molecule, the free radical could be on any of the carbon atoms, and that would seriously affect the products that we could make, and we would end up with a mixture of products. And not only would we perhaps just add a halogen to just the carbon that we've got illustrated on the two possible free radicals here, but then there could be multiple substitution, and it could be on any of the carbons that those further substitutions take place. So just something to be aware of when doing free radical substitution, that typically they will ask you for a specific product, and that's what you focus on. So like on the previous slide, a specific product was 1-chloropropane. It could have been 2-chloropropane they asked about. I would have had to have done it slightly differently. I would have had the free radical on the middle carbon, and we would have had a hydrogen removed there. So they will give you a specific product that they want you to do, but just be mindful that there are other products, and that can feature in other types of questions where they slightly extend what you've just done. But if you have any queries, let me know, and I'll try and sort them out. Thank you.